Okay, so we talked about functions and how in a function, it's a relation where each input has exactly one output. If it's a graph, it passes that vertical line test, which shows you that each input has exactly one output. This video is going to be about the difference between linear and nonlinear functions. Okay, so a linear function, I'm going to fill in some blanks. A linear function is a function whose graph is a straight line, which makes sense. If we look at the word linear, the word line is in the word linear. And the reason they are a straight line is because they have a constant rate of change. So constant means it doesn't change. Okay, it's always the same. Rate of change means slope. So another way of saying this is that the slope is always the same. Okay. Nonlinear functions do not have a constant rate of change. Okay, if you look at different parts of the graph, you look at the little pieces, like the slopes between those pieces are going to constantly be changing, okay, which is what causes it to not be a line. Okay, so linear is a line, has a constant rate of change, slope is always the same. Okay, and then nonlinear functions do not have a constant rate of change. So we're going to look at a couple scenarios. We have graphs, equations, and tables, and looking at the difference between our linear functions and our nonlinear functions. Okay, the graphs are the easiest one in my opinion, because you are just looking to see, does it form a line or not? So linear functions form a line. It could be a diagonal line. It could also be a horizontal line, like so. I'm going to throw that in there. What it cannot be is vertical. Okay, vertical is that straight up and down, because that is not a function. Okay, so that is the only case of a line that is not a linear function for the sake of not being a function. Okay, so diagonal or horizontal lines. Nonlinear functions is a curve. Okay, and those curves can look different. We have something like the first one where it starts in the bottom and kind of squiggles and goes up to the top. Our second graph is that U shape, which we actually call a parabola, which you don't need to know, but it's definitely a curve. So a nonlinear function is just going to be a graph that's a function, but it's curved. It's not just a straight line. Our equations, okay, you have to look a little bit more at these to decide. So for our linear functions, it's usually going to be in that y equals mx plus b form, okay, or y equals just a number, because that's the way we write our horizontal lines actually. The second one, even though it doesn't look like y equals mx plus b, technically we could rewrite it as y equals 1/3 x, and then it would be in y equals mx plus b form. Our m would be 1/3 and our b would just be 0. Okay, what will probably be easier is determining if something is nonlinear, because there's certain things that we look for that kind of says, hey, this is a nonlinear function instead. And that would be something like if the x has an exponent. So something like x squared or x to the third or x to the fourth would be any exponent. But anytime the x isn't just an x anymore and it's x to some power, that's going to be nonlinear. If the x is in the denominator of a fraction, okay, or if we have a square root, okay, that will be a nonlinear graph. And also if x is is the exponent of a number. So 3 to the power of x, that will be a nonlinear function. Okay, so when you're deciding if an equation is a linear function or not, like I said, look for those things that would make it nonlinear. And if it's not one of those, it's probably a good chance that it's linear. Okay, and our tables are going to involve a little bit of math, not tons, but a little bit. So we're going to look at what happens to our x's and our y's as we go across our table. Sometimes our numbers are in order, which makes things easier. Sometimes they kind of skip ahead, which means we have to do a little bit more on that one. But let's take a look at these examples. So we're going to start with our linear side. So we know it's going to be linear, but let's see why it is linear. So as we look at our x's, I'm going to draw a bunch of arrows here. Okay, so -1 to 0, it goes up by 1. And 0 to 1 also goes up by 1. And we can see as we work our way across this table, all of our x's are going up by 1, which makes this a pretty easy one to see. Okay, because now we're going to look at our y values. So from 3 to 6, it went up by 3. 6 to 9 was 3. 9 to 12 was 3. And 12 to 15 was 3. So our x's, because they moved at a constant rate, we can now see that our y's are also moving at a constant rate. Okay, and this would be a linear function because the rate of change is always the same. We could actually take it a step further and say the slope of this is going to be the change in the y's over the change in the x's. The y's changed by 3, the x's changed by 1. So our slope of this table would actually be 3. Okay, let's look at the bottom one. Here are x's, our x goes by 2, and then by 2. We got a 3 and a 3. Okay, so this one here, it's not going the same rate on the top anymore. So we're gonna have to do a little bit more here and see. But let's look at our y. So 3 to 11 goes up 8. 11 to 19 goes up 8. 19 to 31 is up 12. And 31 to 43 is also up 12. So the same thing happens for like the first two sections. And the same thing happens for the last two, but we have to see if those two different things are the same. So if we look at this rate of change for the first, so we have the y's going up by 8 and the x is going up by 2. And 8 over 2 is 4. And for the other piece, we have the y's changing by 12 and the x is changing by 3. And if we set that up as a rise and a run, change in y's over change in x's, it also equals 4. So even though the change wasn't constant across the graph, when we looked at that ratio of rise over run, change in y's to change in x's, it was still the same for that entire table. So something like this, you're going to like set this up as your fractions and make sure they're all equal. In this case, they all equaled 4, so we were good. It's a constant rate of change. Okay, let's look at our nonlinear graphs. Okay, over here, or sorry, our nonlinear tables, I should say. So up 1, and up 1. Okay, so easy one to see. Here for our y's, as our x's went up by 1, they went up by 2, and then they went up by 3, and then they went up by 4. So our x's are all going up at a constant rate, but our y's are changing differently. It went up 2, then up 3, then up 4. It's because these numbers are different. Okay, this would make it a nonlinear function. Okay, not a constant rate of change. Okay, and then for this last one, okay, 1 to 4 goes up 3, and then up 3, and then up 3. So not going up by 1, but at least it's still changed. The x's are still changing at a constant rate, so that's nice. Okay, but our y's are up 15, and then, oh boy, up 33. Took me a second there, up 33, and then up 51. So as our x's went up by 3s, our y's were going up by different amounts. So once again, this is not a constant rate of change, okay, because of this right here and the fact that our 3, 3, 3 on top was doing the same thing each time. So our x's were doing the same thing, but our y's were not. Okay, that's how we know it's nonlinear. Okay, so we're going to do some practice with this and refer back to this chart if you need help.